This video is going to be a polar bond in under 10 minutes. All right. Again, to keep it as brief as I can, the periodic table, you can watch the other videos about, we're going to use oxygen and hydrogen in this example, but the periodic table, you can figure out how we get the number of protons and electrons and neutrons and how to draw these Bohr's or orbital models as we go. So let's talk about polarity. What I mean by polarity is if you have a AA or a AAA battery at home in the remote for your TV or in your clicker or whatever, one side of it's going to be positive, one side of it's going to be negative. So when we're talking about molecules and one part of that molecule has a different charge than the other one, that's what polarity is. So let's look at what causes that, and then we'll talk about a hydrogen bond, which is the kind we're going to draw. And towards the end, I'll talk about the specificities between it. So first, let's go ahead and draw this oxygen. So oxygen, of course, in its first orbital, the 2n squared is going to the equation for figuring out how many electrons are in there. It's going to tell us there's 2 electrons in the first orbital, and in its outside orbital, 2n squared says that in the outside orbital can hold 8. But if we look at how many electrons there are 8 electrons, which means 2 of them are there, and we only have 6 remaining. So in its valence shell, there are 6 electrons, which means oxygen by itself is stabilized, not good, which if there's another oxygen, it'll bind to another oxygen and become H2, the air we breathe. That was in the covalent bonding video as an example. Now, in this case, too, aside from another like an oxygen, the most abundant element in the universe is hydrogen. So one thing that can do is this can grab onto a hydrogen molecule. So let's draw this hydrogen molecule up here. All right, so here we have a hydrogen molecule. We can see that the hydrogen molecule only has 1 proton. All right, so that 1 proton right there isn't enough to fulfill the octet rule for this oxygen, but it's the most abundant element. So what can actually happen is we can have another hydrogen with its proton, and both of these very abundant in nature, and you can probably already see where we're going with this molecule right here. So this electron can inhabit the orbital of this oxygen's valence shell. This electron can inhabit the orbital shell of that. So I'm going to redraw them a little bit with the bond, the covalent bond that has occurred. And I'm going to draw this as the hydrogen. There is that electron that's being shared. And this hydrogen, and there is that electron that's being shared. It is still a covalent bond because each of these elements is sharing the electrons in the exact same way. This hydrogen right here only needs 2 because the first orbital can only hold 2. So this electron right there, we can move this and go like this. And what we see is they're each sharing an electron from each other so that this hydrogen is now stable and it's contributing to there. And again, we'll do that on this side to demonstrate. Right there. So now if we look at it, even though it's against the octet rule, we can only put 2 in this valence shell of the hydrogen. But we satisfy that by 1, 2 for that one there. We satisfy it for this one there. 1, 2, that one there. And now we got 1, 2, 3, 4, 5, 6, 7, 8 in that inside of that oxygen. So both of them are have their valence shell satisfied. And remember, where most people get a little bit mistaken on this is they think it's unequal sharing, but no. This hydrogen is sharing 1 oxygen from there, 1 electron from that oxygen, and this hydrogen is sharing 1 electron from that oxygen, and vice versa. So each of these is 1 single covalent bond. It's 1 pair of electrons being shared between the 2 of them. All right. Now, what you can see here is what is happening is these electrons, even this hydrogen, it only had the 1 electron, that electron is being pulled closer to the oxygen so that oxygen is kind of like stealing all the electrons. If that oxygen is stealing all of the electrons, that means there's more negativity on the side of the oxygen. And if there's more negativity on the side of the oxygen, it means there's more positivity on the side of the hydrogen. Pardon me. So what happens is on this side where these electrons are being pulled down to this, so let's just draw a rendering of what the real molecule might look like in nature. And keeping these in mind, what we're going to see here is the electricity, because you have a hydrogen over here and a hydrogen over here, the electricity, more negativity is being pulled down to this side. There's more electrons in this side than there are in that side. So what happens is this molecule has an end that is positive and an end that is slightly positive, an end that is slightly negative. Very similar to what you would see in your batteries at home, you have this molecule right there with the oxygen and the two hydrogens right there creating this molecule right there. And of course, most of us have probably already figured out that this is H2O or water. And that is polarity, because this is a molecule. One side of it tends to be more positive, which is the side with the hydrogens, because the electrons are all being pulled towards the oxygen, and that side of it tends to be electrically negative. So you have that part there. And I think of it as a pair, and the bell at the bottom of the pair is the more positive side. So that is polarity. That molecule is a polar molecule. Oftentimes, polarity is dictated by hydrogens because it's the most abundant element in nature. And so we know that water, in all of the solutions, water's everywhere. So we have a bunch of these little pear-shaped structures that we got going on right there. And remember, if we're drawing it there, it's a plus and a negative and a negative. Well, just like your battery at home, if you were to take some kind of a electronic mechanism where it takes 3 AAA batteries, you put them in the remote in such a way so that the positive end touches the negative end of the other battery. All right, and if you go home and try that, if you don't understand what I mean. So what we have in water is, of course, you don't have one molecule. You have many, many molecules of water. And so what we end up seeing here is there will be one molecule of water, another one here. Now remember, what's going on here is these will position themselves in such a way as the batteries at home. So here's 3 H2O molecules. So these molecules themselves do not co-inhabit the same area, the same space. But what they are held together is by this bond that's created from this positive end right here. I'm going to get rid of this one so that we have a little bit of space to draw the bond. And this negative end there. Now, because of that, just like the battery in your remote at home, that will form a bond right there. That the polar molecule forms a bond. And in the case right here, because it's hydrogen that's causing this polarity, if I draw another one here, again, we'll come up here and draw the positive and the negative. There's a covalent bond that forms there, which this we call a hydrogen bond. And this idea of polarity and hydrogen bonding is what gives water a lot of its properties of life. So this is a special type of covalent bond called a polar bond. So that's polar bonding in under 10 minutes.